So the next topic we'll discuss is the thermodynamic potentials. So from the first law of thermodynamics we know that it is basically a restatement of the conservation of energy and the transformation of energy in a process. And we know that from the first law of thermodynamics that energy cannot be destroyed, it can be transferred from one form to another. Now one limitation of first law of thermodynamics is that it cannot tell us in which direction any process will take place. And so that was taken care of by the second law of thermodynamics, which tells us about the directionality of a process, that all the natural or spontaneous processes occur in such a direction that the entropy of the system increases. Okay. So it may appear from the second law of thermodynamics that all the natural processes that occur, in all of them the entropy will always increase. Okay, but it is the case is not necessarily so. Okay, so there might be other, because it is this condition that the condition of increasing entropy is not enough for a process to occur. Okay, so these two laws are not enough. These two laws are not enough to give us a general condition for a process to occur. Okay, because these two laws do not consider the fact that all the systems tend to go towards the natural state of stable equilibrium. Okay, so these two laws do not give complete information about the system, so that we can decide that whether the system will undergo any such and such process or not. Okay, so and these are not enough to establish a general condition for a change to take place in a system. Okay, so depending only these two laws, we cannot say that whether any system will undergo any process or not. Suppose the second law of thermodynamics tells us that all the processes where entropy increases, those are permissible, but that is not the only condition for a process to occur. Okay, because so these laws are not enough. Why? Because these two laws do not consider the state of equilibrium, state of equilibrium of a system. Okay, so what is the general condition on which we can depend to decide whether any system will undergo any process or not, a particular process or not? So the general condition is that all the systems have a natural tendency to be in a stable state of equilibrium. Now if you remember the mechanics, then we have seen that any system in mechanics wants to be in a state of minimum potential energy. Okay, so here also if we consider any thermodynamic system, then when any thermodynamic system, all thermodynamic system wants to be in a stable state of equilibrium. So similarly, just like in mechanics, all the thermodynamic system, they will also try to have some minimum potential energy. So this potential energy is applicable for the mechanics. So there is, for a thermodynamic system, there is some similar properties of any thermodynamic system that we can term them as thermodynamic potential. That is, they play the same role as potential energy in thermodynamics. Okay, so what are those properties? Those properties are the internal energy, Helmholtz free energy, Gibbs free energy, and enthalpy. Okay, so these are the thermodynamic potential for a thermodynamic system. Okay, so any thermodynamic system always try to have minimum of internal energy or Helmholtz free energy and Gibbs free energy and enthalpy. And depending on this potential energies, this thermodynamic potential, any system will undergo a process. Okay, undergo any process. Okay, so these four thermodynamic potentials are function of four natural variables, which are pressure, volume, temperature, and entropy. So the first thermodynamic potential is the internal energy. So we know that internal energy is denoted by U. Okay, So now let us we'll find an expression for the internal energy. So let us consider an infinitesimal process during which delta Q amount of heat enters the system and temperature T. So as a result there will be a change in entropy, let it be delta S. Okay. So if delta Q amount of heat enters the system at temperature T and if corresponding change in entropy is delta S, then from Clausius inequality we can say that delta S is greater or equal to delta Q by T. Okay. Or we can say that this is delta S. T delta S is greater or equal to delta Q. Or if we rearrange, we can write delta Q is less or equal to T delta S. Suppose this is equation 1. So now if as the system undergoes this kind of process, is absorbed a delta Q amount of heat, let's say there is a change in internal energy and the volume. Okay, so let's say delta U and delta V be the corresponding change in internal energy and volume. Okay, then from the first law of thermodynamics we can say that delta Q is equals to delta U plus P delta V. Okay, so you already know this. Let's say this is equation 1. So now what we'll do, we'll replace delta Q in equation 1 from the value of delta Q from equation 2. So we can say that putting value of delta Q from equation 2 in equation 1. So putting value of delta Q from equation 2 in equation 1, we have delta U plus P delta V is less or equal to T delta S, or delta U is less or equal to T delta S minus P delta V. Okay, so this is the expression for change in internal energy for an infinitesimal process. Okay, so as usually the inequality sign holds for a irreversible process and the equality sign holds for a reversible process. Okay, so we can write for an infinitesimal irreversible process, delta U is less than T delta S minus P delta V, and for an infinitesimal reversible process, the equality holds and it will be delta U equals to T delta S minus P delta V. Okay, so we already know that internal energy is a state function. So delta U will be an exact differential. Okay, so from this relation we can say that this delta U is a function of two independent variables S and V. Okay, so the above equation, from the above equation we can say that U, internal energy U, is a function of two independent variables entropy S and volume V. Okay, so we can write U is a function of entropy S and volume V. Okay, so if for an isentropic process, which is delta S equals to 0 and isochoric process, that is delta V equals to 0, what we have? We have delta U is less or equal to 0. Okay, so if the process is reversible, then delta U equals to 0 for an isentropic and isochoric process, then there will be no change in internal energy. And if the process is irreversible, then delta U is less than 0, that is there will be a change in, there will be a decrease in internal energy. So we can say that for a reversible isentropic isochoric process, delta U equals to 0, that is during such process there is no change in internal energy.